This is the practice for tonight, or the post lab. So the first thing it says to do is to figure out the balanced chemical equation. So we were working with HKC8H4O4 plus, because we were adding the base and the acid. So don't worry about the phenolphthalein. That's not something that's taking part in the actual reaction. Rather, it's just telling us what's happening based off the color. So that's why we don't include the phenolphthalein here. We have the acid, which is this thing over here, and we have the base, which is this thing over there. One of the things that happens here is we have an acid which wants to give away its H, or its proton, and a base which usually wants to accept it. And in accepting a base, it often breaks up itself. So one of the things that happens when an acid and a base mix is they actually create water. So you can sort of see it already. You have an OH there, and you have an H there. So this actually ends up making HOH, or water. Now what do you have left? Well, you have the component ions that are left over. So if OH is a -1, that means whatever Na is, it's a +1. And then if HKC8H4O4 is a 0 charge, and we remove one H from it, which is this one, then that means whatever is left over is a -1 charge. So we shouldn't go about breaking things up and making it 8 C's and 4 H's and on and on. Rather, think of it as a polyatomic anion, meaning that the H to the left is a +1 charge. So whatever left over, that is a polyatomic anion, that's a -1 charge. So we have KC8H4O4, and that's a -1. Now we wouldn't necessarily put the Na +1 and the KC8H4O4 -1 together because they're ions. So when they're in water, as they are in this case, they're actually in their ionic forms and not completely together. So that's the reason why it is that way. So that is the balanced chemical equation that you have for it. For the calculated data table, we're going to have to go back to what we actually did. So in order to figure out the moles of this HK on and on, this is just the acid. So from here on out, I'm going to call this acid, and I'm going to call this base. So that's easier to say. So in order to figure out the moles of the acid, we have to figure out how many milliliters we used. So I'm going to give you guys sort of a fake trial with easy numbers so that you can put it to the trials that you did. So let's say that we used 5 milliliters of the acid. So when we actually made this acid, we knew something. We knew that it had a molarity of 0.1 molar of HKC8H4O4. So if we know the volume that we used, 5 milliliters, if we can convert this into liters, which is just a for every statement, what we end up getting is 0.005 liters. We can figure out how many moles were used by putting another for every statement. So for every, we use the molarity that we have here, 0.1 moles of acid, there are 1 liter. And that's the case you always have with molarity, period. So as soon as we see 0.1 molar, we write out that for every statement. However, we find that we didn't use 1 liter. We used 5 milliliters in this fake trial. So it's not 1 liter, it's 0.005 liters. So now we're trying to figure out how many moles of acid are there in 0.005 liters. So 1 times 0.005 gives you that. So we have to multiply by 0.005. 0.1 times 0.005 gives you 0.0005 moles. So that means in the 5 milliliters of the acid that we used in this fake trial, there were 0.0005 moles in there. So now we have to think of something else. How do we figure out the moles of NaOH used? Well, we can see that when we poured 5 milliliters, the color of the water changed from purple to clear. What that means is that at that point, the number of moles of the acid and the number of moles of the base were equal to one another. So at 5 milliliters of use, that means that's how many moles there were of the NaOH. So if we find out the moles of the acid, which is 0.005, that is the number of moles of the NaOH, because that's when they became neutral, and that's why the color changed from purple to clear. So now if we know the moles of NaOH, which is 0.0005, we have to figure out the molarity. And this is going to depend on which trial we did. So remember that in trial 1, which is what we'll use right now, we used 2.5 milliliters of NaOH. This is the same thing as saying 0.0025 liters of it. So now we know the moles and we know the liters. So let's set up another for every statement. So for every 0.0005 moles of NaOH, there are 0.0025 liters. This is just what we have right now, because the moles of acid is equal to the moles of base, and in trial 1 we used 2.5 milliliters of the base. So that's all we wrote down. However, this doesn't give us the molarity of the base, because molarity has to be in a for every statement where it ends in 1. And in order to do that, we would have to multiply by 400. So whatever we do to that side, we would also do to this side, multiply by 400. And what we would get is a 0.2 mole there are 1 liter. When you have a for every statement that has so many moles for 1 liter, the most important part being this 1 liter part, whatever amount of moles you actually have, that is the molarity. So in this test fake trial, what we find is that the molarity of this NaOH is 0.2 big M. Big M stands for molarity. So first we figured out the balanced equation. We figured out the moles of the acid based off of how much we had to use to make a clear liquid. The number of moles of acid used is also equal to the number of moles of base used. Once we know the number of moles of the base, and depending on the trial, whether it was 2.5, 5, 7.5, or 10 milliliters of the base, we can figure out the new molarity, and in that case that would be the molarity of the base used. So you're obviously using all of this information with the numbers that you got from your trial, and it's going to be different, and you're going to figure out what the molarity of NaOH is based off of all of your trials.